Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're continuing our examination of amino acids. Last scribblecast lecture, we examined what made an amino acid either acidic, neutral, or basic. We discovered that the differentiating group, the R group or side group of the amino acid determines whether it's acidic, neutral, basic. We also defined a new term called the isoelectric point. The isoelectric point is that point at which the Zwitter ion predominates. We discovered in acidic amino acids the isoelectric point is close to 3. In neutral amino acids, the isoelectric point is somewhere between 5 and 6.3. And for basic amino acids, the isoelectric point is approximately in the range of 7.5 to 10 for pH. Now, in order to examine all of the amino acids and assign their type, we need to go back and look at the amino acids individually, and we're going to do that. Most of the time, our examination is going to focus looking on the R side chain, the chain that determines what the amino acid is. In some cases, however, it will be worthwhile to examine the isoelectric point, and we will do so. So let us begin. We're going to look first at the amino acid alanine. We will not necessarily be looking at all these amino acids in alphabetical order. So let's draw alanine. Here is the amino acid fragment of the molecule, the NH2CHCO2H. And after that, off of the CH, we have our R side chain. For alanine, it's a CH3. Now, CH3 is an alkyl group. Hydrogens bound to carbon are not acidic, nor are there any lone pairs of carbon for it to be basic. Alkyl groups as side chains are neutral, and so alanine is obviously a neutral amino acid. Now, in fact, we can apply this generally to all amino acids that have alkyl group side chains, including hydrogen. So if we continue down our list and examine the R group side chains, we see glycine, the only amino acid that does not have a chiral carbon. Glycine places an H off of the carbon. The H off of carbon is not acidic, nor is there a lone pair to be basic, so this is neutral. And look at some other amino acids that have alkyl side chains. For example, isoleucine. Isoleucine, remember, was an essential amino acid. Do you recall what that means? An essential amino acid is one that you cannot synthesize but must be obtained in the diet. I'll asterisk the essential amino acids. Isoleucine has an alkyl side chain. Do you remember what group it is? That's right, it was a sec-butyl or a 2-butyl. There we go. And then there's leucine, which is also an essential amino acid. Leucine does not have a sec-butyl, but rather, as its side chain, leucine possesses an isobutyl. Okay, both of these sec-butyl and isobutyl are alkyl groups without lone pairs, no acidic protons, so we have all neutral amino acids. Now, if I continue down my list, the only other amino acid in the 20 amino acids common to biological systems is another essential amino acid called valine. Valine has an alkyl group attached to the CH. And that alkyl group is an isopropyl. And that makes it a neutral amino acid. Okay, so there are 5 amino acids, and their common feature is that as R group side chains, they have alkyl groups, and because of that, they're all neutral amino acids. Let's take a look at a unique amino acid, and just for the enjoyment of it, we're going to also look at its isoelectric point. That amino acid is arginine. Arginine is a unique one, and in some ways it's the hardest one to remember because it has a very complex side chain. There are several amino acids that have complex side chains, a little harder to remember. I'll try to point out some features that will help you to memorize its structure. Always remember arginine has 3 CH2 groups. Now this can be confusing with lysine, which has 4, but arginine has 3. And then off of the 3 CH2s you have an NH, a C, an NH2, and off of the C is a double bond to an NH. If you remember this, you won't have any difficulty. It's an interesting pattern, but it's sort of like a acetone fragment with nitrogens in place of carbons and a nitrogen in place of an oxygen. You'll notice what I mean. If I say CH3C double bond O, here's acetone. Well, it's just like replacing those 2 carbons with N's. Of course, you have different amounts of hydrogens because of what's bonded to it. And then instead of a double bond O, you have a double bond NH. Okay. Well, first, let's see if we can decide whether this fragment is going to be acidic, basic, or neutral. And what I'm going to do is I'm going to focus on this end. So I'm going to redraw this. And what we're going to do is examine what happens if it acted like a base. See, amines typically have lone pairs which allow them to act as a base. Except in this case, there's a lot of lone pairs. Now, if we remember our basic chemistry, this nitrogen has 1 lone pair and 3 atoms attached to it, so it's sp cubed. This nitrogen has 3 atoms, 1 lone pair, hybrid orbital number is 4, sp cubed. And this nitrogen with the double bond has 2 atoms and a lone pair, that's hybrid orbital number or steric number 3, it's sp squared. So We have a lone pair in an sp cubed orbital, another lone pair in an sp cubed orbital, and a lone pair in an sp squared orbital. Now if you recall, the more p character, the more diffuse the hybridized orbital, because p orbitals reach further out into space. That means the sp cubed orbitals stick further out. Now, if you don't have the same reach, that's like being held closer to the nucleus. That's like being more electronegative. So the sp squared orbital is held closer to the nucleus. It's less available for protonation. Typically, imine lone pairs are less basic. Okay, well, let's take an examination then of what happens if we protonate different lone pairs. For example, if I protonate this lone pair, well, I get an isolated positive charge here, and that's it. All right, let's go back and put a lone pair back. Let's examine what happens if we protonate at this position. Well, we get this NH3 plus hanging off here, and that's about that. I guess we should just check what happens to the imine if we protonate it here. So I'm going to rub off the sp cubes. What happens if we protonate in this position? All of a sudden, something unique happens. Typically, imines are less basic. But if the positive charge is stabilized by resonance, that can essentially stabilize the protonated species, making the lone pair more likely to pick up a proton. Behold what I can do with these lone pairs on the other nitrogens. I can dump them in to create pi bonds. And I will get a double bond C here. And then this becomes an NH with a lone pair. Becomes a terminal NH2, and I have a positive now here. But that's not the only thing. I can change colors. I could dump this lone pair into there, which would move the pi electrons out. Well, let's draw that one in black so you can... Okay, so now I'd have R and H with its lone pair, C double bond NH2 plus, and this would still be my NH with a lone pair. In other words, there are 3 resonance contributors into which I can delocalize this positive charge over 3 atoms. The net result of that is the obtaining of the positive charge is stabilized. Now, if I make getting the positive charge more likely, more favorable, that means picking up the protons more favorable. That means this molecule is more basic. Okay, well, how much more basic? Remember our isoelectric point? Okay. Our isoelectric point range for basic amino acids, it was what? A range of pH of 7.5 to 10. What is the pi value? The isoelectric point for arginine. Well, if I was to take the fully protonated form and begin deprotonating, I would start with a positive here, a 2 plus. When I deprotonated, I would get a 1 plus. So it's after pKa2 that I would get the zwitterion, and you should draw out the full equilibria for these and see that. So there are 3 pKa values for this molecule. An isoelectric point equals 1/2 multiplied by the addition of the 2 pKs that surround the zwitterion. In this case, it's pKa2 plus pKa3. What is pKa2 and pKa3 for arginine? Well, in this case, it's 1/2 9.04 plus 12.48. If I add these together, I get 1/2. Okay. So 8 and 4 is 12, 4, 5, 21.52. So 1, okay. 2 goes into 15 7 times, 10.76. Wow. That's at the high end of our range. Remember, we've said 7.5 to, I believe, 10. This makes arginine, because of these resonance structures, one of the most basic amino acids. So arginine is a basic amino acid. Okay, let's press on and now look at asparagine and glutamine, because they have very similar structures. Asparagine and glutamine. Okay, asparagine has an H2N CH CO2H, and off of this we have a CH2, a C double bond O, and an NH2. If we draw glutamine, compare glutamine to this, glutamine's only difference is it has 2 CH2s. Then the C double bond O and the NH2. Both asparagine and glutamine have this amide functional group. It has an NH2. So if I focus on this amide functional group, I can redraw that. NH2s have lone pairs, and as we've seen in the case of arginine, we can protonate lone pairs. So for example, I could envisage putting this here and put a positive. But I have a problem now. The N with the positive is tetravalent, has 8 electrons around it. There's no way to dump electrons by resonance towards the nitrogen. There's no orbitals to put them in. Hence there's no resonance structures. Hence the positive charge is only on nitrogen. Okay. And to make things even worse, when there's a lone pair there, I can actually dump the lone pair towards the carbon and draw this minor resonance contributor. Now, it may be a minor resonance contributor, but it's still suggests that there is some partial double bond character between the carbon and nitrogen. Further, it suggests that this lone pair is partially tied up in a bond. Now, if the lone pair is partially tied up in a bond, it is less available for protonation. Resonance is making the lone pair not available. Okay, so this fragment is not basic. Well, what about acidic? I mean, is this not similar to, say, a carboxylic acid? Could not the NH2 lose a proton? Well, in actual fact, losing a proton requires stabilization of the negative charge. Carboxylic acid does this. In two ways. First off, the negative charge is on an electronegative oxygen. And secondly, I can resonance stabilize this. And put the negative charge on the other oxygen. So I can essentially do this. Okay. So carboxylic acid is acidic because it's both resonance stabilized and places negative charges on electronegative atoms. Could I not just replace this with NH2 to do the same thing? Well, in actual fact, this combined resonance electronegativity combo for carboxylic acid only makes carboxylic acids a weak acid. Okay, carboxylic acids are not hugely strong acids. Typical PAs are nearly 5. What happens when you put a less electronegative atom and do the same resonance structures? The fact is, nitrogen's just not electronegative enough, even with the resonances, to make it even weakly acidic. So again, not acidic. This means that asparagine and glutamine are neutral. Neutral amino acids. Okay, well, since we've introduced carboxylic acids, why don't we look at some amino acids that have carboxylic acid side chains? And they're based on asparagine and glutamine. They are aspartic acid and glutamic acid. So let's draw aspartic acid. And aspartic acid is just like asparagine. It has one CH2 and then another carboxylic acid group. Glutamic acid just like glutamine is an amino acid with a R group side chain consisting of 2 CH2s. And then our CO2H. Well, as I've already drawn and indicated, this carboxylic acid functional group on the side chain is weakly acidic. And as given by the names, these amino acids are acidic amino acids. Okay. Let's now take a look at a unique amino acid, histidine. Histidine is also an essential amino acid. I hope I haven't been missing indicating which amino acids are essential. Watch for that if I do miss one. Histidine is an essential amino acid. Again, that means it must be consumed in the diet. What's interesting about histidine's structure is I've actually drawn it previously, so I'm going to draw it again as I recall I did previously. And I almost indicated that this is like a molecule with multiple personalities, because there are two reported structures for the histidine molecule. How can one molecule with one name have two different chemical structures? Well, now we can begin to explore this answer while we take a look at whether this molecule is acidic, basic, or neutral. Obviously, the answer to this question can be given to you in the form of a riddle, such as the Joker or the Riddler would ask Batman. When is a different molecule the same? Something to ponder. When is the different molecule the same molecule? Clearly, these two molecules are structurally different. So how can they be the same? Let's focus only on this side chain. And let's consider where we could protonate it. So I'm going to draw it again down here. And we're going to examine, because we have lone pairs, we're going to begin, as with most nitrogen compounds, examining whether it is basic or examine whether it's basic. So we're going to start with this. And we'll have that attached to an R group. Okay, now, I actually take up less space if I just move the R over there. There. Okay, now we have two lone pairs. Once again, we have an sp cubed nitrogen and an sp squared nitrogen. Now, the sp squared or imine lone pair is less basic typically. Now, we saw that can be changed by resonance. So let's examine first what happens if I protonate the sp cubed. There is something very, very bad about protonating the sp cubed nitrogen. Do you notice what it is? The lone pair is included in the Huckel number for counting pi electrons and determining if there's aromaticity. 2, 4, 6. 4n plus 2 equals 6 pi electrons. If you solve for that, n equals 1. It's an integer, which means if the lone pair is delocalized into the 2p orbitals, if this guy actually goes sp squared, then we have an aromatic ring. Aromatic aromaticity will lower the availability of this proton towards protonation, which leaves only the sp squared imine. Okay, so I can do this. So what happens if I protonate here? And I get a positive. Well, what's interesting is I can dump this lone pair in here. These pi electrons will become the new lone pair. Well, won't that disrupt aromaticity also? Well, let's take a look by drawing the resonance contributor. So now this becomes a pi. That's still a pi. We have an H here. Now we have a lone pair. Notice sp squared, sp squared, sp squared, sp squared, 2 electrons, 2 electrons. The aromatic ring is retained even though we do this resonance structure. Now, I want you very carefully to look at what happens if I rotate around this carbon R bond. If I swing this nitrogen out towards me and all these atoms into the back, I get, so let's say rotate, I get this. Okay, so there's positive here now. Running out of room, I apologize for that. Notice the R is right next door to the NH. So when I rotate it, the R is here. If I now minus H plus, deprotonate, I get the other structure. Okay, so we can answer two questions with this. One, so going from this structure down was plus H plus. Okay, let's put it on the outside. Okay. The lone pair on the imine portion of the ring can get protonated because it has a resonance contributor. This helps favor the protonation process and increases basicity, sufficient so that this histidine is a basic amino acid. So for both arginine and histidine, we see resonance stabilization of an imine, increasing basicity, making our amino acid basic. But not only that, the protonation and resonance structures are what lead to histidine having what apparently are two different structures. In fact, they are different structures. Because we have shifted, what have we done here? We have shifted pi electrons. We've moved pi. And by taking a proton on and a proton off, we've moved a proton. What do you call it when you shift pi electrons and lone pairs and you move one or more protons? These two structures are different, but they are related. They are tautomers. The process is called tautomerization, and we will look at that more closely later on. We have also covered it already. When are two different structures the same molecule? When they are tautomers, of course. They're different, but histidine can interconvert between them. And so they're the same molecule in the sense that they're both histidine. Even though structurally they are two different structures, they are tautomers. Excellent. Okay. Let's take a look now at another molecule, several other molecules, another essential amino acid This one is called lysine. It is essential. Lysine has one of the longest carbon chains for a side chain. It actually has the longest in the 20 amino acids we're looking at. It has not 3 but 4 CH2s, followed by a simple NH2. Now, that means on the side chain we have a simple amine. Amines are basic. Okay. Typical pKb's are approximately 4. And so lone pair on an amine can get protonated. So no surprises here. Yes, there's no resonance, but it is known for an amine to be basic. So this is a basic amino acid. Just looking quickly at isoelectric point. Okay. Remember we were around 10 something for arginine. It'd be interesting to do a quick calculation for the isoelectric point, Pi, for lysine. Lysine, pKa2 and pKa3 are the pKa's that surround the Zwitter ion, and you can check that out if you wish. If you solve this, and I believe we did lysine last time, we have 8.95 plus 10.53, which gives me 1/2. We have an 8, 14, 19.48. 1/2 of 19.48 equals 9.74. Notice that lysine's not quite as basic as arginine, who had a isoelectric point of around 10.76. So arginine with the 3 resonance structures is much more basic. If you had calculated the histidine's isoelectric point, you would have found a 7.59. So 2 resonance structures of histidine are not as basic as the amino group on the lysine, but 3 resonance contributors less as found in arginine makes it the most basic of the amino acids. Great. The 20 amino acids we're looking at. Okay, let's take a look next at methionine. Another essential amino acid. Methionine is a sulfur-based amino acid. That is, on the side chain it has a sulfur group. It has 2 CH2s. And we have a sulfur. The sulfurs have 2 lone pairs and CH3. Now let me ask you a question. Sulfur in the periodic table is located below what element? It's below oxygen. If we were to replace sulfur with oxygen, we'd have a carbon, oxygen, carbon bond. What kind of functional group that? That is an ether. Are ethers acidic or basic? Well, there's no protons to lose, so they can't be acidic. The lone pair on oxygen is not very basic. They're not known to be good bases. So, this is not basic. Now, what happens in the case of sulfur? Well, as you go down a group, acidity increases and basicity decreases. Therefore, if an ether is not basic, as you go down a group, basicity decreases. If an ether is not basic, a thioether, a sulfur-based ether, is not going to be basic. And so methionine, because of its similarity to ether chemically, is neutral. Okay, I missed one alkyl containing group. I guess it's fair to leave it out from the alkyls because truly it is not a simple alkyl. It has an aromatic off of it. What happens if I take alanine? So let's draw alanine. Alanine, remember, was a CH3, an alkyl. What happens if I take an H and replace it with a phenyl? Okay, move in H, put an aromatic ring. So it is carbon-based, similar to alkyls in that, but we have an aromatic ring. Well, we get phenylalanine. Now, a phenyl group by itself, like alkyl groups, is not acidic, can't pick up protons, it's not basic, so it's neutral. Let's modify this, though, and look at what would happen if we just added an OH here. Well, in actual fact, we're going to hold off looking at that, as well as hold off. Okay. In fact, let's draw the two. I'm not going to look at until the end either cysteine or tyrosine. Tyrosine is just phenylalanine with an OH off of it, off of the aromatic ring. And cysteine, so tyrosine has a CH2 as your R group, phenyl OH. And cysteine has a CH2 SH. We pointed out that as you go down a group, acidity increases. So oxygen with OH isn't very acidic, but SH has some weak acidity to it. We also learned that phenols are weakly acidic. Does this weak acidity, is it sufficient for it to become considered an acidic amino acid? We're going to look at that last. I only mention it because of tyrosine's close relationship to phenylalanine, and you might wonder why I am not examining tyrosine in conjunction with phenylalanine because of the similarities in structure. But we're going to save those two to last. And also, don't forget, phenylalanine is an essential amino acid. Okay, the next one we want to look at is proline. Now, when people draw proline, it has a rather unique structure in all of the 20 important amino acids that we're considering. You glance at it and you say, oh, there's a nitrogen on the ring with a lone pair. There's no pi bond, so it's not tied up in aromaticity. This is just like lysine and amine, so it must be basic. And the mistake they make is that they don't look for the amino acid residue. See, every amino acid must have an NH2, a CH, and a CO2H. Well, where's the amino acid residue? Okay, well, let's draw. Here's a CO2H. That carbon's a COH. So this must be the NH of the amino acid. It is the side chain that determines whether you're neutral, basic, or acidic. So the side chain in this molecule must be this, the bridging CH2s of the ring. Now these CH2s are just like alkyl groups, so perhaps I should have included proline in the alkyls that I was looking at, but these alkenes are neither acidic nor basic, so because of that, proline is neutral. It's only tricky because often people consider the NH as part of the side chain when they shouldn't. So watch for that. The next two amino acids we will consider are serine and threonine. Serine is not essential, but threonine is. Okay, serine and threonine are alcohol-based, and in that way they're related to tyrosine. Serine is similar in structure to cysteine, except instead of a CH2SH, we have a CH2OH. Threonine is rather unique. It has an ethyl group off of the CH, but the oxygen is attached to the first carbon of the ethyl. And so you have a threonine. Now both of these have alcohol groups as side chains, and remember ROH can be deprotonated, but you need extremely powerful bases. Yes, if you deprotonate it, you get a negative charge on a quite electronegative atom, but that charge is not stabilized enough to compare with the acidity of, say, carboxylic acids. In other words, alcohols are not acidic. Yes, they can be deprotonated. Yes, the hydrogen is protic and goes off on and off in water, but remember carboxylic acids had the electronegative oxygen and resonance, and they were just weakly acidic. Alcohols are neutral. So, it looks like, by and large, most of the 20 amino acids are turning out to be neutral amino acids. What about another molecule that has a side chain that's often hard to remember? That is tryptophan. Tryptophan, like threonine, is an essential amino acid. And I'm going to draw it a little differently so it's a little easier to see. It has an aromatic ring fused with a 5-membered ring, double bond, and H lone pair. Okay, and then we have a CH2, and we have a CH CO2H. Don't worry, because of the presence of only one nitrogen, there is no histidine effect. Notice I have not been drawing my amino acids in the Zwitter ion. You should note that the Zwitter ion certainly is the predominant form. Okay, well, we've got a lone pair. This is like an amine. Certainly, sp cubed, we can protonate it, right? Well, in actual fact, no. Just like the case in histidine, this lone pair is tied up in an aromatic ring. We have 2, 4, 6, 8, and if we count the lone pair, we get 10 electrons. 10 is a Huckel number of electrons. If you saw 4n plus 2 equals 10, you get an integer. Because of that, this lone pair is delocalized into the pi cloud, giving the ring structure aromaticity, making it less available for protonation. As a result, due to aromaticity, the amino acid tryptophan is neutral. Well, now that just leaves cysteine and tyrosine. So, I'm going to draw them. We've got cysteine. Cysteine is not essential. And we have over here tyrosine. And cysteine, remember, has this structure. The side chain is a thiol, an SH group off of a CH. Oops, that should be just one. CH2 with a SH. Tyrosine has a CH2 with an aromatic ring and an OH. Now, in our organic chemistry course in the alcohol section, we learned that thiols are weakly acidic. More acidic than alcohols, because as you go down a group, acidity increases due to poor orbital overlap. So this can deprotonate to an S-. And so this molecule has 3 pKa's. When you have the fully protonated form, you have the NH3+. You can deprotonate the CO2H, you can deprotonate the NH3+, and you can deprotonate the SH. Tyrosine, likewise, has a slight increase in acidity above that of a normal alcohol. Phenols are more acidic than normal alcohols because of resonance stabilization of the O- into the aromatic ring. Hence, an increase in acidity from the fully protonated form. NH3+ can deprotonate, CO2H, and the OH on the ring can deprotonate. So both these molecules have 3 pKa values. The question is, even though in terms of organic chemistry we refer to them as weakly acidic, are they considered acidic amino acids? In order to answer that, we should do the isoelectric points. Pi for cysteine. Well, if I start with the fully protonated form, I get a 1+. When I deprotonate the CO2H, I get CO2-. That's my zwitterion after pKa1. So we learned for cysteine that to determine the isoelectric point, I have to do 1/2 pKa1 plus pKa2. Well, there's no way of calculating these values. You have to do the experiment. So such values would be given to you. Cysteine has pKa1 of 1.96 and a pKa2 of 8.18. If I add this together and solve, I get 6 and 8, 14, 10, 11, 9, 10, 10.14. 1/2 of that is 5.07. Let's try the isoelectric point for tyrosine. Okay. Tyrosine also starts with 1+ species, so the zwitterion is after pKa1, so we have to use 1/2 pKa1 plus pKa2. If I do this, 1/2 pKa1 plus pKa2 equals 1/2 pKa1 for tyrosine is 2.2. pKa2 for tyrosine is 9.11. I get 1/2, add that up, I get 0.31, 11.31. So if I divide by 2, I get 5.6. 11 is 5.5, or roughly 5.66. And so you see that the isoelectric points found in the 5 to 6 region typical of neutral amino acids. Yes, they're down in pH. They're close. They're in the more acidic end of the neutral amino acids, but they're still in the neutral range. So cysteine and tyrosine are considered, because of their isoelectric points, to be neutral, in spite of the fact that we have presented these in first semester as weakly acidic groups. Consider for amino acids that they're so weak that they're still behaving as neutral amino acids. So there you have it, all 20 amino acids. I hope I haven't missed any. By and large, the vast majority of the 20 are neutral. "15 of them, as a matter of fact. Only aspartic acid and glutamic acid were acidic amino acids, and arginine, histidine, and lysine were basic amino acids. Well, I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening. Please don't hesitate to contact me if you have any questions. You can catch me at the end of class or email me. My email address is bloyd@mhc.ab.ca. That's BLLOYD @mhc.ab.ca. Thank you very much.